So one other time we talked about the law of conservation of energy. And we said that the law of conservation of energy says that energy can neither be created nor destroyed in any physical or chemical process. So right now I want to look at that in terms of a physical process, and that would be kicking a football, or a soccer ball, or hitting a volleyball, or anything that you might want to think of. We call this projectile motion. So this is really a little bit of a physics lesson that I'm sneaking in, but we'll transition into chemistry in just a minute. So let's say that you have this object right here, and you're either going to kick it or throw it or do something to it so that it goes up in the air, and we'll follow its path. It's here, then it gets to the top, and then it comes down. So there's our projectile, whatever kind of ball you want to imagine that is, going up in the air and coming down in the air. Now, at first, if we think of it as maybe laying on the ground to begin with, so let's say that this is a kick. Here, give you some of my fancy artwork. There's a foot that's going to kick that ball. Yeah, that's as far as we want to go with that. So the foot's going to kick the ball and it's going to go up in the air. So right here, it has no potential energy, certainly no gravitational potential energy. We won't consider this a fuel that can be burned out, because maybe it can be, but let's not talk about that right now. So no potential gravitational energy, and it's also not moving, and so there's no kinetic energy, because again, for the moment, we're not going to think about all the individual molecules moving around. Just the ball as a whole is not moving. So no energy right there. Now, after it gets going up into the air, anytime that it's moving, it's going to have some kinetic energy. So if we were to represent kinetic energy, let's put a big KE right there. As it goes up, it's going to slow down, isn't it? And then for just a very small moment in time, kinetic energy will actually be zero, because this is the point where it's changing direction. So even if it's only for one little microsecond, it actually doesn't have any kinetic energy right there. It's going up and up and up. But what happens to its kinetic energy on the way up? Is it's slowing down, right? So if it's slowing down, it's getting less and less and less kinetic energy. So I might say its position here, I'll represent kinetic energy with a really big KE, and then its position here, we'll have a small KE. So kinetic energy is getting smaller and smaller and smaller until right up there it has none. And then on the way down, let's put another one here where we can give it that amount of kinetic energy. And you'll learn in physics that if these two are at the same height, they have the same amount of kinetic energy, meaning the ball is going at the same speed. So kinetic energy gets less and less and less, and then more and more and more. Now, is energy being destroyed on the way up and energy being created on the way down? No, no, no. We know we can't do that. So now we need to talk about potential energy. Remember that potential energy is greater the farther you go up from the surface of the ground. So up here, you're going to have a really big potential energy, but no kinetic energy. And here, you're going to have a fairly big potential energy, because it's still pretty far off the ground, but potential energy will be getting less and less as you get closer to the ground. So potential energy is growing because we're getting it lifted up above the ground, and potential energy is going to have to shrink on this side. Potential energy less and less and less, until when we finally hit the ground, well, let's see, probably kind of messed that up, didn't I? Because when we finally hit the ground, we're back to zero. So let's do that. So no potential energy because we're on the ground, which I didn't draw in. We'll draw the ground here. No potential energy because we're on the ground. No kinetic energy because it's not moving. Lots of potential energy because we're way above the ground, but no kinetic energy because just for that little microsecond, it's not really moving anymore. Potential energy getting more and more and more, less and less and less. Kinetic energy getting less and less and less, more and more and more. But what can we say about the sum of potential plus kinetic at any point? we would say that it's the same at all points because energy cannot be created or destroyed. So at all points along here, we have the same amount of energy, just in different forms. So let's look at that in something that's more closely related to chemistry. Here I have a glass of ice water. So I took ice out of the freezer and water out of the tap. So the water was fairly warm, probably room temperature, and the ice was much colder. And now if I stick my finger into it, I find that the water is much colder than it was to begin with. So what happened? It will be scientific and call that H2O. So if the water starts out warmer and the ice starts out colder, this sounds totally obvious, I know, but this is a real familiar example of something that hopefully you can transfer this knowledge to all kinds of other examples. Heat will always flow from where there's more heat to where there's less heat. Thermal energy always moves from where there's more to where there's less. So it's a little bit like diffusion or osmosis, like that. So heat energy then is going to come out of the water and into the ice cubes. So if heat energy comes out of the water, now the water has less heat than it used to. The molecules are going to move more slowly and the temperature is going to go down. Now, what if I made the water even warmer? Would the heat transfer be faster or slower or stay the same? That's something that we're going to learn about in lab, so I'm not going to give that away right now. But you might, just from your own personal knowledge of how things work, be able to figure that out. Now we have a couple of vocabulary words here. Endothermic. An endothermic process is one that absorbs heat. So, what's absorbing heat? The ice cube's absorbing heat. So the ice melting is an endothermic process. It happens because the ice absorbs some heat. An exothermic process is one that releases heat. So what's releasing heat here? Well, the water's releasing heat. The water that starts out kind of warm and gets colder, that's letting heat leave itself to go do something, to go melt the ice. So now the water doesn't have as much heat as it used to because the heat left the water. Same thing would happen as if you took the warm water and just stuck it in the refrigerator. Now it's cold outside, heat's going to leave. So from the perspective of the water, we've got an exothermic process going on. So our two everyday, very common things here have new vocabulary words associated with them. If heat is going into it, it's an endothermic process. If heat is coming out of it, that's an exothermic process. So let's look at another example. There are some chemicals that you can stir into water and they will make the water colder. Have you ever used an ice pack? Not the kind of ice pack that the nurse has in her office that she keeps in the freezer, but the kind of ice pack that's probably in a first aid kit someplace that doesn't have to be kept cold. And it kind of looks like a bag, and you shake it up and you break something inside. And what you're actually breaking is a little pouch of water. So now that water mixes with the chemicals and the chemicals start dissolving, and when that happens, the water gets colder. So we would call that a cold pack. Dissolving the chemical makes water colder. So usually when we talk about these kinds of processes, we're not that much interested in what's happening to the chemical. We're really interested in what's happening to the water. I want the water to get colder so that I can put this thing on my sprained ankle and the swelling will go down. So let's think about, maybe we'll just put this in a beaker for now. So there's our beaker with some water in it, and we have this chemical down here that's slowly dissolving. And as it's dissolving, the temperature is going down. So we would say that this is an endothermic process. Because the chemical is absorbing heat energy. So we tend to talk about things from the perspective of the chemical, even though we're really interested in what's going on with the water. So we can say that the exothermic process is the water getting colder. And that's an exothermic process because the water is releasing heat so that the chemical can use it to dissolve. The chemical needs that heat in order to do the dissolving process. So the endothermic process is the chemical absorbing heat or the chemical dissolving. The exothermic process is the water getting colder. So if someone says to you, when this chemical, it's called ammonium nitrate, by the way, when ammonium nitrate dissolves in water, is that endothermic or exothermic? They're probably wanting you to focus on the dissolving part, and the dissolving part absorbs heat. And when it absorbs heat, now here's another one of those transitions. Thermal energy gets changed into chemical energy. So the thermal energy is not just going to a different place, it's actually becoming a different form of energy when this happens. So thermal energy gets changed into chemical energy. The chemical process is using heat. We call that endothermic. Where the exothermic process is simply the water getting colder. But usually if you're talking about the dissolving process, this is what you would want to focus on, even though in the case of an ice pack, this is what we're really interested in. We want that water to get colder. We want that water to give up heat. We want that heat to become some other form of energy so that the cold pack will be cold. Now we can use another example, something that I'm really familiar with because I make up lots of solutions of sodium hydroxide. Now you can try this at home if you have any Drano at home. Drano is mostly sodium hydroxide with some pieces of aluminum in it. And you probably know what happens when you put that down the drain. It goes into the water, and then you're supposed to add some water to the drain, and you get all this fizzing, and you can tell that it's getting hot down there. So the dissolving of sodium hydroxide does just the opposite thing. That releases heat. So let's take this, we'll make ourselves another little beaker here. Put our sodium hydroxide in the bottom, we'll show it dissolving into the water. And when that happens, the temperature of the water is going to go up. It's going to get very, very warm. So how can we talk about this process? The dissolving process is an exothermic process. Exothermic process is the dissolving process, and what's happening now is that some chemical energy is being transformed into heat energy. So the sodium hydroxide has less chemical energy in the dissolved form than it does in the solid form. Now that's our exothermic process. Our endothermic process, so remember, this has to be something that endothermic is absorbing heat, so now this is the water. The water undergoes an endothermic process because it absorbs the heat that the sodium hydroxide is releasing. So we'll say the water getting warmer. And hopefully that makes sense to you. Now let's talk about some other examples, like changes of state. Changes of state. So we have things like melting and freezing. Melting and freezing are just opposite processes. So if you take ice at exactly 0 degrees Celsius, it's going to be at its melting point and simultaneously at its freezing point, right? Because the melting point and the freezing point is the same thing. So we'll have a little bit of melting going on and a little bit of freezing going on, and both will be happening at the same time. One of those is an endothermic process. One of those is an exothermic process. Can you think of which is which? Which process requires heat in order for it to happen? Which process makes the ice cube absorb heat? Well, the melting, right? So that's endothermic. So our ice cube is undergoing an endothermic process when it melts, and it's undergoing an exothermic process when it freezes. Did you know that? When water freezes, it releases heat. When water melts, it absorbs heat. So if you were able to keep it right at 0 degrees, you would have both of these things happening, and you would be releasing and absorbing the same amount of heat because you would have these two things happening at the same rate. So there would be no net change. You wouldn't be able to see anything happening, but there would be actually lots of things happening. You would have some melting, and you would have some freezing, you would have some absorbing of heat, and you would have some releasing of heat, but all in the same amounts, so no net change. We can do the same thing if we think about something boiling, because in order to make it boil, you need to bring energy into it. So heat energy is going to be absorbed by the water, and it's going to boil and become steam. And then if the steam condenses and becomes water again, it will release energy. So the same idea as this, just a different phase change.